Welcome to the fourth lecture in the series of lectures on Galilean Laws of Motion by DHS Maithripala. So in this lecture, what we will do is look at this quantity that appeared in this expression over here. So we saw that if R is a special orthogonal matrix that relates two orthonormal frames, then its derivative is related to R by a skew-symmetric matrix, or in other words, R transpose R dot is a skew-symmetric matrix. And we saw in the previous slides, when you try to compute the equations of motion in a moving or rotating frame, this quantity omega hat played a big role. So we will look at this quantity omega a little more closely and find that it is actually the angular velocity of the frame B with respect to the frame E. So let's again look at what this is. So omega hat is a skew-symmetric matrix. The most general skew-symmetric matrix has only three independent elements. Its diagonal is 0. So if you have omega 1 here, minus omega 1 here, this is omega 1, omega 2, minus omega 2, and minus omega 3, then this is omega 3. So we will denote the space of all such 3 by 3 skew-symmetric matrices by the small case SO3. This is the standard notation used for representing this space of matrices. And what we notice is that this is a three-dimensional vector space. Why? There are only three independent elements, and you add any two skew-symmetric matrices, you get another skew-symmetric matrix. You multiply a skew-symmetric matrix with a real scalar value, then you get again another skew-symmetric matrix. Therefore, the space of all possible skew-symmetric matrices are a vector space under over the real numbers. And since it is three-dimensional, we know that it can be identified with R3, which is the most fundamental three-dimensional vector space that we have. So in other words, this is what I just said. So if you get three ordered numbers, the ordered triple of numbers or element of R3, you can construct a skew-symmetric matrix using this recipe over here. You take omega 1, make it minus, put it there. You take omega 2, put it there. You take omega 3, multiply by minus 1 and put it there. Then you make it skew-symmetric by making this omega 1, making this minus omega 2, and making this omega 3. So that is the way of constructing a skew-symmetric matrix from an element in R3. So we will formally say that this hat is a map from R3 to SO3. And this is how that map is defined. So you take an element in R3, you construct a skew-symmetric matrix, and that construction is denoted by this hat, and we will call this a hat map. And it is easy to show that it is linear, it is one-to-one and on-to map. What we are interested in is actually finding out. So we saw that R dot is equal to R omega hat. Omega hat is a skew-symmetric matrix. Any skew-symmetric matrix can be written like this. Given a skew-symmetric matrix, it can be identified with an ordered triple of numbers. What we are now interested in is actually whether there is some physical significance to this quantity. That is, you have this omega hat. What is the significance of omega hat? Or alternatively, is there a physical significance of the corresponding R3 element if you construct it this way? That's what we are going to look at in the next few slides. So we will begin by looking at a few basic examples. We now have here a frame, two frames, the E frame and the B frame. The B frame is actually rotating about the E1 axis. So the E1 and the B1 axis are fixed, and it is rotating in the counterclockwise direction by an angle θ1. So you could imagine this as spinning about axis B1. Now, if you write down the two relationship between the B and the E frame, we have something like this in the usual notation that we have been using in this class. What this means is it's a rotation about the one axis by an angle θ1. And if you write it explicitly, we find that that is given by this. So this you would have done in one of your assignments also, and I also talked about this in a previous lecture. So let's alternatively look at another example where now the B frame is rotating about the B2 axis, or E2, B2 axis are the same, and it is spinning about this axis at a counterclockwise, in a counterclockwise direction, theta 2. So then again, B is related to E by a rotation matrix where the 2 axis is fixed and it is rotating with an angle theta 2 about the 2 axis. So if you write it down again, we find that this matrix is given by, explicitly given by this expression only. Similarly, if you have a B frame that is rotating about the B3 E3 axis, so it is rotating about E3, and B3 and E3 are the same, and it is rotating by an angle theta 3, then we can write it like this. Now, if this angle is changing, so or if all these things are spinning about the axis, theta 1 is changing with time, theta 2 is changing with time, theta 3 is changing with time. So if you differentiate these matrices R1, R2, R3 and multiply by R1 transpose and multiply R2 dot by R2 transpose, and if you multiply R3 dot by R3 transpose, what do we get? We can do this calculation directly, and we find that R1 transpose R1 dot is given by this, and we will call that omega 1 hat. And if you take R2 transpose R2 dot, we get omega 2 hat to be given by this. R3 transpose R3 dot to be given by this. Now let's construct using the hat map and going back and forth between the hat and the skew symmetric and the R3 version. We will construct the R3 version of this, and we find that the R3 version, so the omega 1, the R3 version is given by this expression over here. And omega 2 is given by that, and omega 3 is given by that. So now if you look at omega 1, omega 2, omega 3, it is very interesting. Why? Because this shows that, well, this frame B is actually rotating about the 1 axis. This frame is rotating about the 1 axis at a rate of theta 1 dot. And that's what this says, 1 axis theta 1 dot. This frame is rotating about the 2 axis at a rate theta 2 dot. And that is what this thing is saying. This frame is rotating about the 3rd axis at a rate of theta 3 dot, and that is what this says. So in this particular example, we have seen that omega 1, omega 2, omega 3, actually the omega that corresponds to the omega hat in the R dot is equal to R omega hat expression is actually the angular velocity of the B frame with respect to the E frame. Now these are 3 very special examples. In the following few slides, what I will show is that it actually holds in general as well. But before we do that, we will just look at a few more properties of the hat map, because we will need them in order to show this in general. So for any 3 R3 elements, X, Y, omega, we can easily show that you take omega, get the hat map, which is a 3 by 3 skew symmetric matrix. You multiply by X, which is a 3 by 1 matrix, which is equal to the omega cross X. So we have in R3 a well-defined notion of this cross product. We have a very nice relationship between the cross product and this hat map times X. So in order to find the cross between omega and X, all what we need to do is get omega, skew symmetric size it, get a 3 by 3 matrix, multiply it by X, and that answer is equal to B. Again, we have also, it is easy to find that if you get the inner product between X and Y, then that is equal to minus 1/2 of the trace of X hat times Y hat. We can also show this R times X cross Y is equal to RX cross RY. Now this is actually easy to think. What does this mean? You get X and Y and cross product it and multiply by R. Answer is same as you multiply X by R and cross product it with R by X. So this actually corresponds to a rigid rotation, and this is a property of R that preserves angles and length. So we will look at this a little more closely in the following slides. Another interesting property of this hat map is you get R and X, multiply them together, you get a 3 by 1 matrix, you get the hat version of that, that is equal to the R times X hat times R transpose. You can also show that x hat squared is equal to this. So these expressions, these three expressions will play a crucial role. These will play a crucial role in our computations that we will be doing subsequently, and also in terms of understanding what this omega matrix is, or in terms convince ourselves that omega is actually the angular velocity of a frame rotating with respect to another frame. Using this expression, we will also, it is easy to show because by multiplying it by another x hat over here, that this thing holds, multiplying it again by x hat, that this thing holds, and this thing holds, and so on. So the odd powers are something times x hat, and the even powers are something times x hat square, and that continues for all this. And this will also be very useful later on. So I just put it here as a property of the that is significant property that we should keep in mind. So let's now look at the following situation. So we have a box, and the box, and there's a frame, E frame. The E frame is fixed to earth, and the box is actually free to move, but initially the box is in an orientation as shown in this figure. So these edges align along this axis, and this vertex is at this point. And what we will do is we will fix a frame B to the box, so that the B3 axis is along this edge, B1 axis is along that edge, and B2 axis is along this edge. So initially the E and the B frame coincide. So the box is in a orientation as shown here. Now let's think of rotating the box while keeping this point fixed. So we will leave that point of the vertex of the box fixed and rotate it. And let's look at what happens to this point. So now this point will be at a new position with respect to the E frame. But if you look at it from the B frame, it is at the same position. So if you can just visualize this. In the B frame, it is this. So if you rotate the whole box, and if you fix the B frame also to the box, in the B frame, this point remains fixed. So initially, if you represent the point P using the E frame, you have EX. X is how much along E1, how much along E2, and how much along E3. Since E and B frames are initially coinciding, the B frame representation of the point is also the same, simple. Now let's look at what has happened to the representation of the 2 points in the 2 frames. Now in the B frame, it is the same, but not so in the E frame. Why? Because the point is now changed in the E frame. So we will write this new point, new position of the same point after the rotation of the box. And so in the B frame, nothing has happened because the B frame is fixed to the box. So it still appears to be in the same place when you view it in the B frame. So in the B frame, the representation of the point P, the new representation of the point P, which we call PR, is still given by simple X. Whereas if you look at it from the B frame, it is given by a new position, because the position of this has now actually changed because the box is rotated. Now, what is the relationship between XR and X? That's again, we have seen this, how we have seen how to do this. So the B and the E frame are related by a special orthogonal matrix R. So if you plug that thing over here for B, you plug in ER, you plug that thing there, then you get this. So this says that the new position of the point seen in the E frame is equal to R times X. So what has this done? So what this has done is R has, or the rotation that relates, the rotation, so the special orthogonal matrix that relates the B frame to the E frame has really transformed this point, which was at X, with a representation X, to a new point XR when you view it in the E frame. So R maps, what R has done is taken this point and given a new point by simply multiplying by R. And let's take again a little closer look at what that map does. So what I'm saying here is rotating the box. Every point in the box is equivalent to really multiplying every point in the box with respect to the B frame by R. So that's what we see. So all the new points as you see in the E frame are equal to the old points times R. So all points, all multiplied by R, you get a set of new points. That's what this is. So it's R is a map from R3 to R3. It takes R3 points and gives you again R3 points. Let's look at what these properties are. So again, using those properties that I talked about in the previous slide, you can show that Rx minus Ry. So what does that mean? You have 2 points, PR and QR. So PR has representation R times X, and QR has representation R times Y. So the distance between PR and QR is given by Rx minus Ry. Now using the properties of the special orthogonal matrix, in particular this property, you can show that this is the same. So in other words, the distance between P and Q before rotation is the same as the distance between P and Q after rotation. Again, if you find the angle between X and Y, the rotation between the angle between X and Y is the same as the angle between the rotated X and rotated Y. So what does this tell you? This tells you that this map that takes points in R3 and gives you a new point in R3 is a map that takes points by rigid rotation. So in other words, lengths are preserved and angles are preserved. So R can be thought of as an action on R3, acting on points in R3 to give new points in such a way that lengths are preserved and angles are preserved. So that's one way. So we have now seen two ways of looking at R. One is R can be a special orthogonal matrix, can be thought of as an action on R3. Another thing that we saw from the beginning is R3 can, special orthogonal matrix can be thought of as a relationship between orthonormal frames. So given two orthonormal frames, the orientation, the relationship between them are given by a unique special orthogonal matrix. So those are two distinct meanings of a special orthogonal matrix that we have seen so far. This is the third one. So let's take this point. So we have an E frame and we have another rotated B frame with origin fixed. Now we have some quantity that is fixed. So we will call that that quantity we may represent as an arrow in the E frame, and that arrow will have the representation simple gamma in the E frame. So what does that mean? You draw these perpendiculars to the three axes, you get the lengths along the the lengths to the foot of the perpendiculars along the three axes, put them in a column matrix, that is gamma. Now if you write down the same quantity, same arrow in the B frames, how much along B1, how much along B2, how much along B3, we get capital gamma. And again, we have seen that since B is related to E through ER, you plug that in. So then the relationship between the two representations of the same arrow. Now the arrow is fixed. Arrow is the arrow. But if you write down the arrow in the E frame, you get simple gamma. If you write down it in the B frame, you get capital gamma. So this tells you that R can also be thought of as a coordinate transformation. So you have E frame coordinates, you have B frame coordinates. This is the E frame coordinate, that's the B frame coordinates. So the B frame coordinates are related to the E frame coordinates through this relationship where R is the rotation matrix that relates B to E. So that's a third interpretation that we have seen of R. So let me summarize those three interpretations over here. So this is R can be thought of as the unique matrix. So R is a special orthogonal matrix. A special orthogonal matrix gives you a unique relationship between two orthonormal frames. We saw that. Then we saw that a special orthogonal matrix also acts as a map that takes points to other points through rigid rotations that preserve lengths and angles. Third interpretation is the one that we just saw, where we can see R, the special orthogonal matrix, that as a coordinate transformation between quantities in two orthonormal frames. So this and this are closely related, and this has a very deeper meaning, and so we will try to understand them a little more closely. So let's now imagine the following situation. So we have this point P that is the vertex of the box, and now this box is spinning with this point fixed, and the frame B is fixed to the box, frame E is fixed to Earth, and the box is spinning. So we want to see what happens to these points in the box instantaneously. What are the velocities of those points? Can we find them? Are there any interesting relationships in the instantaneous velocities of the box? So the box is spinning. So this point is changing with time. So what does that mean? So this point has a representation in the B frame, and now that is not changing with time. But this point has a representation in the E frame. Now that is changing with time. Why? All points in the box are changing with respect to E. And let's look at those points and their velocity. So the B frame is changing with time. What that means is R is changing with time. The special orthogonal matrix that relates B to E is changing with time. E is remaining fixed. Now we will write down, we will let omega hat to be R transpose times R dot. And we will write down this point OP R, the new position of the point at the given time t. In the E frame, it will have simple xt. In the B frame, it will have a fixed representation, capital X, but B is equal to ERT. You plug that thing here. Then you get the E frame representation of the point P to be given by R times capital X. So the position of the point can be kept, can be tracked by, if you know the R that relates the B frame to the E frame. You get that R and multiply the position of the point in the B frame, which is fixed, and you get the position of the point as seen in the E frame. Now that's the position. So let's try to see what happens to the velocity of that point in the E frame. So we will just differentiate that. Then you get R dot times X and R times X dot, but X is fixed, so X dot is 0. Now R dot is R omega hat, so you put that in there. But we notice that omega hat is equivalent to the omega cross X. So you have this relationship over here. Then one of the properties that you would also show in the assignment, and I summarized in the previous slides, is that this is equal to R omega cross Rx. So if you look at R as a rigid rotation, what does this tell you? This tells you omega cross X and rotate it is equal to omega rotated, X rotated, and cross it. So well, that makes sense because these are rigid rotation. And we will call this quantity over here R omega, a new thing, simple omega. Now using the coordinate representation, what we find is this new quantity omega is related to this omega through R. Therefore, this is the B frame representation of that and nothing else. So if I write, so Rx I have seen to be X, so I have put that there. R omega I will define to be whatever that you get, the resultant of that to be simple omega. And that is, so according to that definition, what we have is basically that the simple omega is the E frame version of the capital omega in the B frame. So if you look at it from a coordinate change point of view. And so if you write it again, you get this. Now this is very interesting. So what does this tell you? This tells you that the velocity of this point, the instantaneous rate of change of position of the point in the box, any point in the box, is given by omega cross X, and omega is something that is not related to the point. See, it is only related to the rate of rotation of the frame, or the R, and the rate of rotation which is given by this thing over the R3 version of this skew symmetric matrix. Now that is independent of point, but when the points in the box change for different points in the box, this X will change. So all velocities are related to this fixed quantity cross X. Now since X dot, so the velocity is equal to omega cross X, so what does that tell you? So we have this figure over here, but before I come to that, we will notice the following. This tells you that X dot is perpendicular to X, and X dot is also perpendicular to omega. So what does that tell you? So if you, let's draw that omega first, because why is that? It is independent of all the points. It only depends on R and capital omega. And so if you know capital omega, you just multiply by R, you get 3 numbers. You set it out as axis in the E frame. And you also set it out the position of the point in the E frame, X. Now, what does this tell you? Omega cross X is equal to the velocity. That is what this says. Omega, this arrow, omega, in the E frame, cross product with this arrow, which is the point representation of the point in the E-frame, gives you the velocity of that point. So that is very interesting. So what does this tell you? If you take all the points in the box, all points that lie along this, what is the velocity? What is the velocity of all the points in the box that lie along this fixed axis at that point? Fixed in the sense instantaneously fixed point, the axis that does not depend on the points. So all points on this axis will have zero velocity, because why? X will be omega and omega cross omega will be zero. So all points, so this box is rotating instantaneously. If you look at it, all the velocities of all the points in the box along this axis have zero velocity. Also, this tells you, and this perpendicular relationship tells you, that if you think of this point to this arrow to be here, that this point is trying to rotate about this axis instantaneously. So this shows that omega is the angular velocity of the B frame of all these points with respect to the E frame. So it is like the angular velocity of this point. Instantaneously, all points are trying to rotate about this axis, and points along this axis have zero velocity. So it's like the box is instantaneously rotating about that axis. And therefore, so omega is the angular velocity of the box or the frame B with respect to the frame E as observed in the E frame. And then the coordinate representation relationship that we get from here tells you that capital omega is the B frame version of that, the B frame version of that. So let me conclude this lecture by defining a new quantity called the angular momentum. Well, the angular momentum was defined before, but let's try to write it down in the B frame. Because why do you want to do this? Because we saw in some examples that it is convenient to write these things down in a moving frame rather than in the inertial frame. So let's try to find out what the relationship is for the angular momentum in a inertial frame and in a moving frame. So we saw that the positions are related by this, velocities are related by this, and we had a similar expression for accelerations. Now let's write down angular momentum of this point. Well, that's defined by this expression over here. Let's write everything down using the B frame quantities. So that's what we have done over here. And now if you look at this term over here, this term, we can write X cross omega cross X, omega cross X as X hat. This thing can be written as minus X cross omega. So this can be again written as X hat omega. So you can have, we have minus X hat omega squared omega. So if you write that thing down, let me get rid of this first. So we get this term over here. So this term is equal to that. So you guys can verify it at the end of this lecture. So what we will do is define this quantity. Since this appears over here, we will define this MP X hat square, which we saw from one of the previous slides, that can be written down in this fashion, to be the moment of inertia of the point P about the point O prime. So this point particle or point object with mass MP, at this point, we will define IP to be the moment of inertia of the point mass P of mass M about the point O prime. And that is given by this expression over here. Now, if you define that quantity, you can rewrite this thing over here using this. And so what do we get here? We get something, angular momentum of the point P expressed in the E frame is equal to R times something. So what is that something? Well, that something has to be this thing represented in the B frame, nothing else. So using that coordinate interpret. So we will call this whole thing to be the angular momentum of the point P expressed in the